Going to do some physics problems from chapter 8, starting with number 47. Thinking about conservation of energy kind of stuff. Let's see, we got a 75-gram frisbee. Is thrown from a point 1.1 meters above the ground with a speed of 12 meters per second. So here's the ground, here's the point where it's thrown. This is 1.1 meters. And speed of 12 meters per second. When it has reached a height of 2.1 meters per second, did I say a height of 2.1 meters per second? That doesn't make sense. Height of 2.1 meters, sorry. Then it's going 10 and a half meters per second. What's the reduction in mechanical energy of the Frisbee Earth system because of air drag? Well, we just have to find the total mechanical energy from each. So here, this is like the initial energy situation. So we have mechanical energy initial is going to be equal to the mechanical energy final plus the thermal energy that's lost. Those are not equal to each other here. We could go ahead and figure that out, I think, but they're telling us in this problem that that is the case. So we got some mechanical energy here. It is not conserved because there's friction, so then we have mechanical energy here, but it's less by that much. All right, so let's see here. There's two ways you can handle the 1.1 and 2.1. You could just say, okay, I'm going to make this right here equal to height 0, and then here it doesn't have any gravitational potential energy, and here it has 1 meter's worth. Or you can put both. You can put it on both sides and have 1.1 meters worth and 2.1. If you think about the algebra that's going to happen there, it's the same result. So I'm going to do it this way. I like to make whatever lowest point height 0. So that means we have kinetic energy here. It's going to be equal to the gravitational potential here. I think it's important to write out these kind of high-level versions of the equations before you jump into the mathematical models, the 1/2 mv squared and the like. It's m g h, and the h is 1 because if I make this height 0, then this is going to be 1 higher than that. And that thermal energy term there, that's the only thing that I don't know. So time to calculator. So I've got this 1/2 times 0.075 times 12 squared minus 0.075 times 9.8 minus 0.5 times 0.075 times 10.5 squared. So the energy lost there is 0.53 joules. And we could figure that out because we knew everything else. It's hard to figure out how much energy is lost if you're missing any information at all. Let's see, let's just do a quick check, make sure we're good there. Yep. Number 49, a 25 kilogram bear slides from rest 12 meters down a lodgepole pine tree, moving with a speed of 5.6 meters per second just before hitting the ground. So the bear is going to start here. I don't really know how to draw a bear. And then end up here. This is 12 meters. And the bear's final velocity is 5.6 meters per second. All right. What change occurs in the gravitational potential energy of the bare Earth system during the slide? So the change in gravitational potential energy is mg times the change in height. So that's equal to mass of bear times 9.8. And the change in height is going from here to here. That is a negative change in height. He's losing height. So gotta make sure you get that negative sign in there. So whatever that is, 25 times 9.8 times 12, 2,940 joules lost of gravitational potential energy. That's part A. What is the kinetic energy of the bear just before hitting the ground? Right, so a measly 392 joules. So what does that mean? It means that the if this is how much was lost and this is how much kinetic energy was gained, I'm going to write an equation similar to this one just so I don't have to balance too much of the positives and negatives and all that. So I'm going to write an equation that says here at the top the bear has gravitational potential energy, and then at the bottom he's lost that, but he's gained kinetic energy, and then whatever thermal energy that's lost there. So this is the positive version of that, right? This is the change in from this side to this side. So we have 2,940 is equal to 392 plus that thermal energy. And so what do we have? 2940 minus that 392. So about 2550. And then the frictional force, well, the work done by friction is equal to force times distance, this like average force. So that's the idea. If this energy, if the friction is going to tap this much energy out of the system, that's work done by that friction force. So 2,550 is equal to the average frictional force times that distance. So about 210 newtons of bear on pole friction. Let's see if we got the right answers. We sure did. A little bit different choices about rounding, but all good. So where's my sheet that says that 53 is the next one? Let's see, in figure 850, got the classic block on spring here. A 3.5 kilogram block is accelerated from rest by a compressed spring. There's a spring constant of 640. Block leaves the spring at the spring's relaxed length and travels over a horizontal floor with a coefficient of friction of 0.25. The frictional force stops the block at a distance of 7.8 meters. All right. All right, so the spring constant here is 640. We don't know how much it was compressed. I think we are looking for that in part C eventually. Don't know how much it's compressed. I do know that the mass of this is 3.5 kilograms. And I know that on this rough floor here that the coefficient of friction is 0.25. They put a K there. I'm not going to subscript it just because there's only one kind of friction here, so it's kinetic friction. I'm okay with that. So, and this distance, stopping distance, is 7.8 meters. All right, so what can we figure out here? Well, the work done by friction is what stopped it. So that frictional force is mu times mg, right? Mu times remember that friction, the force of friction is equal to mu times the normal force. And since this is just flat, the normal force is just the weight, mg, of the block. So mu mgd, I think I've got all that stuff. So let's see, mu mgd. About 67 joules. That's all the energy that was lost. Friction tapping it out of the system, doing that negative work. Is that what? Is that the answer for part A? Yes. So the increase in thermal energy is that, because it was lost from the block's kinetic energy. What was the maximum kinetic energy of the block? Well, it was that, right? Because that's what had to be tapped out of the system. So kinetic energy max, or initial if you want, like at the equilibrium spot where it loses contact with the spring, is going to be 67 joules. And then where did that kinetic energy come from? Well, the spring, when the spring was all loaded up, we had the potential energy in the spring. That's where that, I'll be consistent there, that's where that kinetic energy came from. So that's 1/2 k x squared. And I think that's going to let us solve for our compression. So let's see if we can get a right answer there. So I got a compression of about 46 centimeters. Let's see how we did. 53, this is. Oh boy. Rock and roll. 55. Got another block spring situation, but this time the block's headed toward the spring. Same kinetic coefficient, 0.25. All right, so it's headed in, what is this, 55? The block is headed toward the spring. It's, well, we don't know its speed yet. We know its mass is 2.5 kilograms. We know the spring constant is 320. Half the spring it used to be. When the block stops, it has compressed the spring by 7.5 centimeters. That's that compression we're going to use in the 1/2 kx squared. Coefficient of kinetic friction. Boy, this is a lot like the last one, isn't it? All right. Okay, so they want to know first in part A, what's the work done by the spring force? Well, you just want to be careful. Actually, let's be clear here. This was work done by a spring is the negative of that, like delta spring energy. So we just want to make sure that we do have the right sign. If we're just thinking about, like, okay, I'm going to do 1/2 kx squared, obviously, at 1/2 kx squared. But should it be positive or negative? What is the spring doing in this situation? Is it doing positive or negative work? Think about that for a second. I'm going to push some buttons on my calculator. I think you can just think about that as is the spring adding energy into or taking energy away from the block? It's taking energy away from the block, so it's doing negative work. And you can see that here because how that would work. So that's I got negative 0.90 joules. In part B, what is the increase in thermal energy of the block floor system? Quiet here for a second. Slides on when the block stops. Oh, okay. So sorry, I was wondering, like I felt like we didn't have enough information because we didn't know how far it's sliding here. But they're asking us while the block is in contact with the spring and being brought to rest. So that frictional force, they're only talking about this little stretch right here. So the work done by friction is equal to, so friction would also do negative work, but the increase, they're asking what's the increase in thermal energy. So that's the positive version of that. So I guess we could say, if we wanted to be really fussy about this, we could say that's negative force of friction times distance, which is negative mu mg d, which is negative 0.25 times 2.5 times 9.8 times 0.075. So friction does negative 0.46 joules worth of work. So that means the delta, the change in thermal energy, can't make mistakes with that pencil, is the positive version of that. Right? The thermal energy has increased because of the friction. That's always going to be true. Friction doesn't make things cooler. What is the block speed just before when it reaches the spring? Okay, so these are what's happening to the block is the energy, the work. You could cast this in terms of work or energy. I think I'm going to say that the spring potential energy, where is that coming from? Well, there's work done here, right, that was tapped out of the system, and then friction tapped this much out. I guess I would think that understanding the signs, the positives and negatives here, is probably the trickiest thing about this problem. Oh, we already know. Oh, sorry. They're asking, and this is all the kinetic energy, not that US, that's just this, right? So, sorry about that. We already did that. So anyway, that doesn't change what I was saying there, that the trickiest thing is maybe just understanding how to manage these signs. So I think that if you think about, okay, this block had kinetic energy and then it gave it up to these things. If you think about, like, where's the energy here before, where's the energy here after, then all those things, all those quantities will be positive. You're looking for the sum total of where's all the energy at before, where's all the energy at after. And if you do it that way, I think that's, and have everything positive in this final version of your equation, I think that's the best way to manage all that. It's the only V, I guess I'll just leave it unsubscripted. So what's my V? Looks like the square root of 1.04 meters per second. Let's check that. That's good. And 57. Ooh, this looks like fun. Got a block here. And this, that's for going from start to finish. It does go below that, but I don't think I really care about that because I'm not going to be doing so. I think that if I remember this problem right, we're not doing anything there. This is some height 1.1 meters. Initial speed is 6. And coefficient of kinetic friction here is 0.6. And it's going to skid along some distance d. And they just want to know what that d is. All right, so here I've got all kinetic energy. So there's different ways. I guess the highest level version of the equation could be our initial mechanical energy here is going to be equal to our final mechanical energy. That would be the end of it if there were no non-conservative forces, but there is friction up here, so that's plus the energy that's lost to friction there. So here, if this is my height 0, then all I've got here is kinetic energy. And then if I've stopped here, then I have some gravitational potential energy because I've gone up 1.1 meters, and the work done by friction, the positive version of the work done by friction. So you could just say that's the frictional force times that distance. Nice way to fill in the details there. So here I've got 1/2. I think I know the mass of this block, and I didn't write it down. It is... no, I don't. Oh, so maybe it's just going to cancel out because it's in all the terms. So let's see how that looks. 1/2 m v squared is equal to m g H plus mu m g d. All right, so indeed. So it looks like D. I think we talked about this recently in some other video, or I talked about it, and you hopefully listened. How much work you want to show after this, that's really up to you. This is the important, like, physics communication. And I feel like some of us are we have that flipped upside down. Like, you're really interested in showing me all of your arithmetic and algebra, and, I really don't care about looking at that. What I need to see is that you understand the physics concepts. That's the important thing to communicate. So let's see. Subtract that. And divide by that. Well, that's what I got. I'm not going to show you any of my arithmetic. And looks like my arithmetic was okay. So one more, 59. A stone with a weight of 5.92, weight, force of gravity, mg, that's what that means. You would, just in case you need to know what the mass of it is, you divide that by 9.8, right? 5.29 divided by 9.8 is, that's 0.54 kilograms. It is launched vertically from ground level with an initial speed of 20 meters per second from the ground. And the air drag on it is 0.265 newtons throughout the flight. So the force of friction, that's what air drag is, it's a frictional force. It's constant, that's, that would be some kind of very rough approximation because air drag is not constant, but they're telling us in this case to assume that it is. What are the maximum height reached by the stone and what's its speed just before it hits the ground? Okay, so let's see what we got here. Here's the ground. It's going to get launched up. It's going to come back down again. We want to know what its maximum height is. Let's just call that h max for now. So here at the ground, we have its initial mechanical energy, and then I'm going to call this final for now, up at the top. And we are losing energy to friction. Right? You see that that's a typical form of things there. If there's no friction, no non-conservative forces, then mechanical energy is conserved, right? But there is in this one. So my mechanical energy at the ground is just its kinetic energy, and then that's all going to gravitational potential. No kinetic there because it's the peak. And then the thermal energy, which is the, sorry, let me be consistent with what I did the last time here. That's that work done by friction. So kinetic energy, 1/2 mv squared equals mg h plus the friction force times the distance, force times distance. The distance is the height. So that height is the only missing thing there. is what I've got there. And then on this side, so it looks like that height is going to be, I'm going to call that 19.4 meters. And how about the maximum speed just before it hits the ground? Okay, so then now I'm going to say that its initial mechanical energy is at the top. So this is from the bottom to the top. And then now I'm going to go from the top back down. And we're going to lose more energy to friction because it's still traveling through the air, rubbing up against that air. So now at the top, I've got my mg8. I've got my gravitational potential. It's going to get to the ground with some kinetic energy, but we've lost more to friction. So let's see, I've got mg8, which we just found was 19.4, is equal to, I think a little smashed up in this corner here, kinetic energy 1/2 m v is what I'm looking for, squared, plus that force times distance. We know what the force is. They told us it's 0.265 times the distance we found in part A. All right, so sorry about the congestion there. I'm going to do some math. Well, I'm going to push some buttons on my calculator. I'm nearly there. I hope I pushed all those buttons right. I got 19.0 meters per second, which kind of makes sense, right? It would if we launched it up at 20 meters per second, then went up, came back down again. It's if there was no friction, then we would expect it to return to the ground with the exact same velocity that it left with. Let's see how we did. That was number 59. We're good. All right. You got some pizza coming your way.